Hello and welcome back to Calculus 2. We are going to talk about differential equations. Chapter 9, they have 5 sections, but because there is differential equations course, we are not going to go through all of the details that they have in those 5 sections. We are only going to take a look at small amount of stuff that you just, need to have an idea of what these things are. So we are going to start with the definition of differential equation, which will say differential equation contains function, not function. Let's start with independent variable first. So contains
kind of like implicit differentiation.
Independent variable, yes. Function and its derivatives. Make sure you put plural on the derivatives because the differential equation could have second derivative and third derivative and so on. We will see that the order of differential equations depends on the higher order of the derivative present. We are going to use the implicit form and we'll put x, y, y prime, y double prime, and then 3 dots and say equal to 0. So something similar to the way we defined derivatives like implicitly in Calc 1. So now, and you will see this notation again once you get to Calc 3 for multivariable function. All right, so now this is a differential equation. And the differential equations, let's see some examples. Let's say y double prime plus y equals 0. Y double prime plus y equal sine t. T being the independent variable. Generally in differential equations, we like to use not x, but t as independent variable because t represents time. So I would like to observe something evolve in time. Population changing in time, distance changing in time for my speed and velocity, right? So these basic ideas in mathematics give rise to physics, physics gives rise to engineering, right? So we generally use the variables. Now, the equations you see over here are actually wave equations, and the solutions to these things would be, sines and cosines and things like that. And now what you see on the bottom down there is you see also something that we call a driving term. So over here is the system that just dangles in space, right, at certain frequency. And over here you have the system that is constantly excited by something. So if you just have a pendulum dangling like this, right? It was started, right, and it just floats in space and dangles left and right. Great. This one over here is a kid on a swing. What is the kid on a swing? It's just a pendulum, right? But then you have someone in the back constantly pushing with the same. So the kid is not going to go higher or faster or anything. The kid is always going to go the same. At the same speed, that goes to the same height and comes back, and there is always the person that pushes at the back, and think of that system forever, right? So that's what this equation describes. Now, in terms of engineering, right, you can translate all of those kind of oscillations into wave-like behavior, so you are going to have all of the radio waves and all of the computer speed in terms of calculation, so you can have your hertz, megahertz, and gigahertz and everything else. So all of these things are in base of these kind of calculations. You also are going to have let's say 3, say you have 3y prime minus 2y equal to 0. That's also a differential equation. You might have x. No, I don't want x. Let's do t's. Let's say you have t squared y double prime plus t y prime plus 3y equal to 0. So all of these are differential equations, and as you can see, they contain independent variable, which would be t in this case. They contain a function, which is y. Y is f of t. So over here, I can say for these two. So let's put it this way. Put two arrows like that, and say y is some function of t. So we know t is the independent variable. If it's not signified, like in the first two, you can have x as independent or t is independent. You can change that if you want. It's fine. My definition up there said x. I could have placed t. It's fine. X or t, whatever. Independent variable. So here is the very important thing, right? These are equations, right? These are equations. So what am I going to have as a solution? And this is something that we write in blood and have to understand. Solution of the differential equation is a function y.
Because you're combining the terms of the function itself. Because you don't know what the function is when you're looking at y prime.
Exactly. When you look at the function, very good, excellent. So when you look at the y double prime plus y, you don't know what that y is.
You're so right.
So our goal is to figure out what y is equal to, and that's what differential equations are for. And now I would like to stop just for a second and tell you how many equations you know so far. You know a lot.
You know what?
You know the linear equations, you know quadratic equations, you know exponential equations, logarithmic equations, trigonometric. All of these equations you have been learning for 5 years, for 10 years so far. What do they all have as an answer?
Y.
A number. A number. Right? Your x plus 2 equals 5, x is 3. X squared equals to 9. X is either negative 3 or positive 3. Every single equation up to today had a number as the answer to it. Welcome to differential equations. Your answers are no longer numbers. Answers are functions. Right? So this is a higher tier creature. Right? Higher tier creature. Where you are taking everything you learned so far and you put everything you learned so far, every equation you learned so far, you put them in a bag and you call those equations equations because their solutions are numbers. X equals 3, x equals pi over 4, x equals 1/3, right? And then the separate bag called differential equations where answers are functions. Y equals sine t, y equal e to the t, y equal 3t squared plus 7, right? So answers are going to be functions now. And I want to immediately go into example and show what I mean by that. You had a question or no? All right. So here is our first differential equation to get our feet wet. Now try to get this sentence in one line, okay? So because we need to translate from words of English into mathematical language, which is equation, and then we'll learn how to solve it. So the sentence is, the change in population in time is proportional to population. So fit that somehow. The change
So p prime over 3.
in population in time is proportional to population. So this is how science is done. 100% of science is done this way. You observe something in nature, in society, right, in the world, and you have language representation of that thing. So you observe this. You know that if there are a lot of rabbits, you wait a little while, you'll have even more rabbits because they multiply like rabbits. If you can do that with mice, you can do that with rats, right? If you have only 2 rabbits and you wait the same amount of time, you're going to have additional rabbit or 2, right? You're not going to add additional 500 rabbits in a year if you have 2 rabbits. But if you have 100 rabbits, yeah, you might add another 500 over the same period of time. So when you observe something like that, it makes sense to say that additional population is proportional to the population that is there now. I mean, you can also look at that with humans. A female, right, can give birth on average to 1 baby a year. I understand there are twins and triplets and 6, whatever they're called when you have 6. But the thing is that a vast majority of females has 1 kid per year. And it's even challenging to keep the trend of 1 kid per year for 10 years and have 10 kids, right? That track record is kind of very difficult to pull off for human females, right? Now, obviously, some animals would have a litter of 10 or 12 puppies or kittens or little piggies or whatever, right? In that case, it's a different species, so it has different physiology. But for humans, right, let's keep it 1 child per year. And it's not going to be 10 consecutive years, right, for 10 kids. Now, so the change of population in time is proportional to population. And I would like to translate this now to mathematical language. So how do we translate the change of population in time? dp over dt. It's a change of population in time is denoted as the derivative, right? And then the word is equal. And then proportional is k. And finally, we have population, we agreed, is p. Look, color-coded. The entire sentence of just a basic observation of nature around you is translated into mathematical equation, which, look, contains a function and its derivative. Hello, differential equation, right? Now we're going to learn some classification as well, so pay attention here. I'm going to have dp dt equals kp. Also, I can write this as p prime equals kp, right? So both of these are okay, but the first one is better because it shows the independent variable t, which tells us that this population changes in respect to time. And we know that, right, for humans it takes about 9 months to cook up a baby. Then let's recuperate, and then you can start the whole process again. So dp dt equals kp. Now, what we are going to say, and this is now new thing that you are learning in classification, you will say that this is the first order differential equation. First order differential equation because it's the first derivative only. So the order, you can write this as a sentence if you want, as a rule. The order of differential equation is equal to the highest order derivative. The order of the differential equation is equal to the highest order derivative. So if you have a seventh order equation, well, that means that the highest derivative in the equation is the seventh derivative. And seventh derivative, remember, it's the 7 in the parentheses. It's not 7 tick marks. It's 7 in parentheses, right? That's that one.
You said highest order derivative?
Yes. Okay. So in this case, you have only first derivative. So this is the first order differential equation.
So it actually have a seventh order derivative?
Depends on polynomial.
Oh yeah, you can have as many as you want. It's just that in application, I've never seen higher than 4, right? For differential equations, and that was in graduate school, I saw the fourth derivative equation. Generally, we go up to the second order. Yes, in differential equations, when you learn the general equations, they are going to put the 6th and the 13th and all, but you will actually not be solving ins and outs of it. It will be actually converted into polynomials, and it will be easy. But for the practical application, you will go the most, to the fourth derivative. Most of our applications are just first and the second, actually. That's the most of our applications. So, what you see here. Now, the second classification for the same differential equation over here is that it's a linear differential equation. Now, this concept is harder to understand. Linear differential equation means that the derivatives are not squared or cubed or anything like that, that there is no multiplication between independent variables and the derivative terms, and so on. So if I am to go here on the list of examples that I gave, the 3 equations are linear equations. So these are linear equations right here. And they are linear because if you take a look at their y's and y primes and y double primes, they do not have any squares on them. They are not multiplied by other functions. There are no product rules or anything like that, okay? The one on the bottom is not linear. It's called non-linear equation, the one that is excluded, because you have t squared times y double prime. So that one would be non-linear. You can have, let's say, another nonlinear equation would be, if you want the nonlinear equations, here, well, let's write more. Y times y double prime plus 3 t equals to 0. That's a nonlinear equation because it's y times y prime. So we have independent variable times the derivative, nonlinear. You have function times the derivative, nonlinear. Here is another one. Maybe you have y prime, everything squared, plus 3t equals 0. Easy to solve, nonlinear. Nonlinear. Let's go with the minus 3t on that one to make it into the real domain. So, the linear versus non-linear is harder to get, but again, it will be very important distinction. You will learn that in your first day of differential equations class about linear versus non-linear. So technically what I am teaching today is your first day of the differential equations course. I'm going to have the same thing next semester when I teach this class. So if you tune in, right, if you stay subbed, you tune in the first, it's going to be this, yes?
Are you saying that first order differential equations must be linear? Or
No,
okay.
Because look on the bottom. This one, this is your first order linear and first order nonlinear. So you have both flavors, and you'll have both flavors of all of them. Also, if you write sine of y prime, that's also going to be nonlinear because y prime is buried within the sign, making it nonlinear, right? So the top 3 equations are linear, the bottom 3 are nonlinear, and there will be infinitely many combinations, right, that you can get in linear and nonlinear. As long as one term is nonlinear, the whole equation becomes nonlinear. So if this t wasn't there, it still would be nonlinear because that t is there. So as long as one term, yeah, it's just like in the society, one person messes up for everyone else. So it's just standard. Okay, so now we understand what differential equations are. We understand they contain derivatives and all these cool things. We understand that the solution for the differential equation has to come up to be a function. We also understand the first order, second order, blah, 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 depending on the order of the derivative you have, the highest order of the derivative. We understand, to some extent, and you'll practice, linear versus nonlinear. One more thing left for the lecture, and that is, let's learn the very basic way to solve differential equations, which is called separation of variables, and we are going to apply that to our dear problem we just had here. So here we go. I'll write, let's say, in purple. I don't use it. We will use separation of variables to solve this problem. Guys, separation of variables is the first and easiest method of solving differential equations that we learn, right? And those equations are not plentiful, right? There's a whole bunch of them, but not too many. You will learn a lot more integrating factor and it's just like the whole differential equation course is different method. So, do we see the title? Separation of, this should be a V, not R. It looks like R, so I'm bothered. Variables. There we go. So, separation of variables. Well, what are the variables that you have in the equation here? What are the variables that you have? P and T, beautiful. P and T. P is the variable for population, and T is the variable for time. Beautiful. So I'm going to separate them, where I'm going to put P's on one pile on the left and T's on one pile on the right. So this will immediately become dP over P is equal to KT. So this is where separation of variables happened. I'll write sep of vars. So you know what happened from the top to the bottom. So you see all of your P's on the left, and we moved, oh, the hell is my D? DT. Yeah, KDT. KDT. I just make sure that I, do that. You have to.
Yeah, I know. It's all right.
You write in pen, so every time I mess up, you have to.
It's all right. I think I'm going to make it.
Such is life, right? All right, so guys, look what I have. I have dP, I have dt, so how do we get rid of those? Right? We integrate both. So please write a new line, and then you will put in the integral signs. So please copy the new line so you know that you added integral signs. What is the integral dP over P? ln absolute P equals to, what is the integral of K dt? That would be K dk. This is K dt. K is a constant.
I mean KT.
KT. Plus C. Okay, so you know what? So far, when you forget plus C, you lose a point. What happens now if you forget plus C?
You lose your life.
Okay, we can go that extreme, you lose your life. Guys, you actually lose the problem, and you will see why. this C is no longer just a little plus C at the end. It could be a part of the solution and a significant part of the solution. Yes?
Well, in lab 1, the first question, we were moving up from acceleration and velocity to displacement.
Yes.
Yeah,
Yes. And and in some sense you were skipping actually over these concepts, but yes, very good. All right. Now I want this, so I'm done, right? I'm done. But we can make it better because I can solve for P. How do I solve for P? Yes, I E both sides. So now I have P as a function of T is going to be E to the KT plus C. So now what I'm going to do is I'm going to break this plus C into a separate E to the C using basic algebraic. You remember the algebra? Hopefully you remember the basic algebra. X to the m times x to the n is x to the m plus n, and then we just read it backwards, right? So that's the equation we use to separate that plus C into its own E. Okay, I got that. So now what? Well, now I'm going to call this thing over here is a constant, right? Constant. And this is where your initial population pops from. And that's why that plus C is so damn important. Do you remember this population equation? Yeah, you do. You've seen it in pre-calc, you've seen it in Calc 1, you've seen it in Calculus 2 for your exam.
Oh.
Yeah, right? That equation is derived from differential equations. No one sat down and said, yeah, it looks like it's this.
Oh my God.
It's derived. All of your physics formulas are derived in this way. All of them.
Oh my God, really?
Yeah.
That makes my
No.
physics homework possible then.
No one ever sat down and say, I think that blah, 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 right? So now, I want to think about this. Remember the sentence. Change in population is proportional to population, and then constant of proportionality was K. What did we say for that K? The more people or the more rabbits, the more babies. Less people or less rabbits, less babies. That's the K part. Now tell me what happens if all of the either rabbits or humans are female. No male. What happens with the population?
Oh, it goes way down.
And let's say they are immortal. They're going to live forever. These females are going to live forever.
Oh, well then
What happens with the population?
No,
It can decrease. No one is going to die ever.
Oh, it's gonna be constant.
Constant, thank you. Now, remember what happened. If all of the rabbits or humans, I don't care which one you want to think about, are either male or female, pick whatever you want, and they are immortal. They can't be killed, all right? They can't be killed. They don't even need to eat. They don't die. They don't age, nothing, right? They're just be. They're there like elves in Lord of the Rings, all right?
There's no change.
There is no change. So the constant K would be 0. Do you see that it kills the entire E term becomes 1? Because E to the 0 would be 1. And what happens then? Your population in time will always be the initial population P0 because there is no change. Now, if I get K not to be 0, now I have a small population, K is small, then the E term is small, and the change in population is small. You will be multiplying P0 by a small number, and then the population change is small. If you have a lot of people, K becomes large, and large K makes the large E term, and when you multiply the large E term into populations P0, when you started from, boom, large population. You see how it works? What happens when K is negative and the population?
They're dying.
Yes, right? Hashtag Japan, Germany, and now US too. So negative population, negative k, means decreasing population, because you will be multiplying p0 with a number that it's less than 1. See, e is 0 at 1, right? When k is 0, and then you let the time pass, right? That's another thing that it's a factor in this. So see how it makes sense, right? It makes sense. It makes sense. So the more people you have, the bigger p0, because that's your initial population. And then also k. K is also the constant between male-female ratio. That's also going to be factored into k, right? 1 female, and let's say, I don't know, 1,000 male. Again, female can have 1 baby per year at most, right? It doesn't have you have 1,000 men. Doesn't matter, right? The k is going to be very small. 1 female, 1,000 male. Your p0 is 1,001, initial population of 1,001. K is ridiculously small. So the next year is going to be population of 1,002, because there will be 1 baby, because 1 female. You asked, what if we reverse? You reverse that. What happens? 1,000 females. Oh, it's a bad example, but okay. Well, 3 times a day. Oh, wow. So now you have 1 male, 1,000 females, right?
Wow.
With the 3,000, with the 3 times a day, right, for the full year, right? You do get 1,000 females pregnant, I guess, and then the population is what? 1,000 females plus another 1,000 babies. So the population is 2,001 now. On the next year, right? Because 2,000 females, 2,000 babies, that's 2,000, and then that 1 guy, right?
Origins child support.
The child support, yeah.
They'll be supporting growth.
Right?
Yeah. Well, you don't want, yeah. Now the guys don't even want to have 1 in the current state of things. So do you see that so the biology of the situation also governs what the k is, and then you have the amount of people, right, that goes into p0. So these are the parameters that all change, and you see how through differential equations we make this alive, right? We make this alive. So that was the population model. We use separation of variables. The next one that I'm going to go and talk about is the physics, because you brought it up. What is acceleration?
Second derivative.
Change of velocity in time, right? And then what is velocity?
Change in position.
Change in position in time. Okay, try to work it out using separation of variables. I'll be right back. I gotta.
difference of ds over dt over dt would be dt squared into d squared d, so difference squared. We're just treating it as d. And you're right, it's making it to dt equal almost ds. Does that make sense? Because it would be ADS. Well, because we're solving for the best way to do it. We solve for A, and keep in mind it's a situation we move around so we have a common term in D. So you could either do it, you could do it either way and then bring it to DB.
Like this one, pretty much, is where we would tell which way we're going to go.
Because really, if you get it one way, you can get it the other way.
Oh wait, no, here we solve the p, because the p is the major function.
No, D to D makes sense because you have B to the DB. So
We
you
need to
can
solve
take the
for,
integral of
we
that.
need to solve for s, because s is the position function. Sure. Well, I mean, the math would still be the same all the way here, I just don't know what we're supposed to have on one side of the equation. I think it's supposed to be s, because s is the position, and in the first one we were solving for population, which is the same thing. It's like the basic function. The only thing that the two things have in common is that so we have to solve for dt and the other one. You can do it through all of them.
Yeah.
Okay, that's just what that end up being B squared over 2 equals AS. Like integral of AS.
Yeah.
So then B squared over 2 should equal A to something. Or it should just equal A.
It would be as, because s is the
Right, you may
variable
remove the
of this one, and a is the constant.
Right.
So then if we're solving for s, then s would equal b squared over 2s, or 2a.
Well then, so you're taking the integral of both sides of this, and then A would also be squared root over 2 and S would just be S.
Well, a is a constant.
Unless you do it by parts at that point. Because you'd have ds and you don't know what S is, so you might have to treat S as such and make it dA. And actually move it around like that.
Oh yeah, a is an equation.
So then you might have to move it around by parts, and then you might have, so that means solving for S might make more sense because, or,
Yeah, I don't know.
because at that point you're doing it by parts. At that point you're taking it, you have two different integrals, or two different variables.
We would be, no, if we integrate a, we get b.
No, yeah, if we integrate A, we get B.
So a ds would be b.
Right, and if we integrate S, we get gibberish. Oh, we end up with S. We end up with S and B essentially.
We get sb. ds. Yeah.
So it can be divided by, you can multiply by 2 and divide by b, and so you get b equals 2s, which would make sense because that would be taking the derivative of the, or of s to become.
Oh, that fucking changes everything. These are functions, and they're all related to each other.
Yeah.
Integrate the derivative of the function. Oh man, that just threw a wrench in my gears. I'm gonna walk around a little bit.
Get those thinking gears flowing.
Yeah.
He's going on by asking questions, figuring the answers, son of a bitch.
What did you guys even take with from that?
So
VDB over DS.
So VDB ds over to a. So then a, the integral of a is going to be a squared over 2.
Oh, so you integrate after you get to that point.
Right.
Is that what you guys do? Yeah.
Because you can.
Yeah.
Oh, actually,
You want to get rid of the.
no, no. A, I don't want it to go. Right here. So if I just control that point, I have that division going on. It would just be v ds.
Both sides, so.
You get a ds.
Yeah, you're right. Integrating by parts.
That's what you just asked him?
No, you're definitely right though.
Because it would be, you would assume that ds would go from ds to s.
So it would be a ds integrating by parts. So we would have to.
It'd be a and ds, but we already have the ds, so ds would come up to s. A would become dA, but you can't get rid of anything that way.
We would have to solve for ds
Unless
and then integrate that.
you do it the other way, because a would come up to velocity.
Now, a would come up to. Yeah, a would come up to velocity. But how would we integrate ds?
Unless
Just-
unless you want to do it from VDV ds to a.
The integral of
No.
ds would just be s.
No, what if you started from here? Because you integrate this to v, and then this right here would be the difference of v times the difference of the inverse of ds. So that way you can move this around a lot easier than you can move this, or than you can move this. So this way this just becomes, let's just say v for simplicity's sake, since we know that acceleration is going to go to velocity. Now that's going to equal, I don't know what v for d would be everything, but dv would be the actual difference, and it's going to be v over ds. And as we know, v already equals ds over dt, so it would be 1 over dt, which becomes dv, dv over dt.
1 over dt. Hang on, I lost you.
So basically, alright, so if we did this, we have dv right here. V, as we already know, equals ds over dt. So if we were to take that, you would rewrite it as ds over, it would be ds over dt dx. So you can cancel that out, and it becomes dv over dt with a still over here. And that equals dv over dt.
ds over dt.
Because v equals ds over dt. So then it's ds over dt over ds, which gets moved up to ds over dt dx, dv.
What do you do?
I'm not even integrating at this point, so we have a equals v equals ds over dt over ds, and then times dv. So then that moves into ds over dt ds by dv up here with it, cancel these out, and dv over dt equals dx equals that. And that's no integration, it's literally just moving the parts around.
Yeah, but what are we solving for then? I think we need to get rid of the D stuff.
That would make sense.
I think that's the whole point of this thing.
What is the whole point? Like,
I think you have to get rid of like the,
I know.
the derivative thing.
got rid of it.
Look, let's take a look at this and then leave. So, A, change of velocity in time. We separate the variables. We have what? dv equals a dt. We integrate the two, and it comes up to be velocity is equal to at plus some constant c. Now you call that constant c initial velocity, and you get your physics formula. Final velocity is initial velocity plus acceleration times time, which you might have learned as Vf minus Vi equals At. I'm not sure which way you learned in physics, but that's the physics formula.
This is a lot easier.
Yeah, like, I don't know.
What are you solving?
So difficult.
What are you solving for in these things?
So if you're taking the integral of a separate function against the difference of a different function or a difference of a variable.
You don't have to think about it. You know that time is a variable, and you also know that acceleration is constant, like acceleration of gravity 9.81, so a is constant. So when I do separation of variables, I have a dv and I have a dt. So those are my variables for the problem. The rest are constants. So now I have,
I hate this so much.
I understand it
Like,
now.
that's like the most just elementary, simplest kinematic equation there is, and I overthought the hell out of it. And that's what that's
Acceleration is a constant. How come works for you?
So,
Yeah, if you integrate
I get it.
acceleration, don't you get velocity?
that's exactly what we did. We integrated acceleration dv dt. dv dt, but see, the trick is that the derivative of velocity is acceleration. So integral of acceleration is velocity. And we integrated and we got velocity on the bottom.
But when you integrate acceleration on the right side,
No, that's a constant. A is a number, is a parameter.
doesn't
It's
mean
not a variable.
acceleration. It's not acceleration.
It is acceleration, but it's constant in the eyes of this problem.
like when you
Something we're not
acceleration
thinking
value,
about.
It's just a number. It's not like a.
You want that
It's
to
like
be,
you're saying that the acceleration is 1 all the time in that case.
well, acceleration, yes. So acceleration for the gravity for the planet is 9.81. Meters per second, yes. So is it going to make it better if I put g, like gravity?
no, I'm gonna get more confused.
There's g, that's g, that's g, that's g. There you go. It's a constant everywhere.
Are you do you use that in a vertical sense?
Yes,
Okay.
I just used it. Right?
But when even if you get g as like the gravity constant, when you like that comes from the derivative of the velocity function.
Yes.
So like if you were to integrate the gravity constant, you would still get a velocity function.
Which I did. Right there.
But wouldn't it be a v on that side too? Like as a function?
No, because the variable is in t, not in a. A is a constant. A is not a function in this case. A is a constant.
Like how would you know that t is your only variable? We've got a's, b's, s's, and d's, and like only t is the variable.
T is the only independent variable. Everything else depends on it because you accelerate in time, you change your position in time, right? You drive it miles per hour, right? So t is the only independent variable.
That makes sense when there's context where, like, okay, we're talking about like acceleration, velocity, and position, and time is is changing. So like, it
Yes.
makes sense in the context of this problem. But if you're just given a bunch of variables equal to each other, and like d whatever, like x equals, how would you know which one is the
Well,
variable?
you have to give it a context. That's what the physics is all about.
So
You
there's
do
always
not,
gonna be some
you never work out physics without a context. You can work math without a context, right? Because math can just pile up a whole bunch of equations and numbers, you're done, right? Well, now is what I'm going to do. I'm going to replace this v, right, for the last step of today. I'm going to replace this v with a change in position in time. So it's going to become ds dt equals to v0 plus at. To separate the variables, I am going to move dt to the other side and integrate. And now we're going to change to get the s of t, which is the position in time, is going to be, and now I
V squared over 2 plus ATV, and then
v0t plus at squared.
v0t plus at squared plus some constant c, and we're going to call that constant c some initial position s0. So we get that s of t is equal to at squared plus v0t plus s0.
Oh yeah, that's
Parabolic, yeah, if you remember, y equals negative 1/2 gt squared plus v0t plus y0, right, from physics. You remember that formula? Well, that's where it comes from.
what is that?
Parabolic motion, when you throw something like this,
Yeah,
the vertical, yes, the vertical component y of where it is.
There's like 4 different functions for projectile motion. Depending on what variables you have, they all come from, I guess, this.
So they all come from here.
Is V0 and S0 is the same? What's the difference between V0 and S0?
So v0 is initial velocity, because you just saw me run an experiment, right? So the difference between v0, last time we went all the way across the room, right? So v0 is how strongly, right, you launch your projectile, and s0 is what height I can throw it from here. S0 is 8 feet. I can throw it from here. This is v0. S0 is 6 feet. You can throw it from here, 4 feet.
So S is basically the position then, and
Mhm.
V is the force.
Yes. S0 is initial position. V0 is initial velocity, initial speed, right, at which you throw. So you've seen differential equations. They are used to derive all of your physics, all of it, right? And the way it works, you observe phenomena, and then you write it out in terms of English language, and then you translate that language into, because you can understand that your speed is the change of position in time, right? Speed is change of position in time. So that's what you say, speed, we can call that v is equal change of position in time. That's a differential equation. We had it up there and we solved it down here, but you take the English words, right, and you translate that into mathematical equations, and then you solve the differential equation to get the model. Cool? Bye.